guys, it's Miss Rye again, and we're going to finish up our physics class with more discussion on wave-particle duality. But today we're going to introduce de Broglie's equation. And our learning target today is I can calculate the de Broglie wavelength of a particle. So we're going to do like we've done before, where we have some basic questions about the video we're about to watch, but I also want you guys to try to calculate this. And remember, you'll need a scientific calculator. If you don't happen to have a scientific calculator, you can also download the app. So we'll watch the video, we'll have a Google form that will be your assignment, and I'll also include some extension opportunities that are optional if you want more. Here we go.
Wave-particle duality is the idea that light and subatomic particles can behave both as waves, but also as particles. Therefore, the two states are not mutually exclusive. A scientist called de Broglie introduced the idea in 1923, and it formed his doctoral dissertation. This might be hard to imagine. How could light be both a wave and a particle? And indeed, physicists found it difficult to accept too. What we needed to be sure of wasn't just mathematics, but we needed actual experimental evidence. We already knew from the 19th century that light could behave as a wave, that it exhibited reflection, refraction, and diffraction. These features couldn't be explained any other way. Then, Einstein's photoelectric effect experiment showed that light could also behave like a particle. It turns out that light contains packets of energy, or quanta, of a particular size. These days we call these packets photons. But that's just about light. To really pin down the more fundamental idea of wave-particle duality, we needed to also show that not only could light behave as a particle, but particles could also behave as waves. In 1928, Clinton Davison did exactly that, in what would later be named the Davison-Germer experiment. In his experiment, he fired electrons at a solid crystal lattice. Some electrons would reflect off the outermost layer of the crystal, while others would reflect off layers further inside the crystal. The electrons that reflected from the lattice were analyzed and turned out to have light and dark fringes in this pattern. What did the pattern mean? Well, the electrons that bounced off different layers had interfered with each other, just like waves. By different electrons penetrating at different distances, this created a path difference between them. Wherever a peak met a peak, or a trough met a trough, he saw a bright spot called constructive interference. And where a peak met a trough, he saw a dark spot called destructive interference. Electrons, it seemed, could behave as waves. Now that it had been shown that particles and waves were one and the same thing, it was time to put some mathematics to it. De Broglie did this as part of his dissertation. He suggested that if something was a particle and a wave, then it must have both a wavelength, like a wave, and a momentum, like a particle, and that these things must be related to one another. According to his equation, the de Broglie wavelength, lambda, of an object or particle measured in meters would be equal to Planck's constant, h, which is just a number that's always equal to 6.63 times 10 to the minus 34, divided by the momentum of the object or particle, p, measured in kilograms meters per second. We can also expand on this by remembering the basic equation for momentum, an equation which states that the momentum of an object or particle is equal to the mass, measured in kilograms, multiplied by the velocity, measured in meters per second. We can try this experiment by calculating the wavelength of an everyday object. For example, a Mini Cooper. What is the wavelength of a 1,000 kilogram Mini Cooper moving at 30 meters per second? First of all, we should write out what we know. We have a mass m, which is 1,000, and a velocity v, which is 30. We also know that Planck's constant is always 6.63 times 10 to the minus 34. So, we can just divide 6.63 times 10 to the minus 34 by the momentum mv, which is 1,000 multiplied by 30. That gives us a wavelength of 2.21 times 10 to the negative 38. This is a minuscule number. So for a Mini Cooper to act like a wave, to diffract, for example, the obstacle it diffracted around would have to be a mere 2.21 times 10 to the negative 38 meters in size. Any bigger and nothing would happen. This is unbelievably tiny. In fact, 1,000 trillion objects this size would reach the width of an electron. As far as we know, no such object even exists, and so that's why a Mini Cooper doesn't appear to act like a wave. Wave-particle duality is the idea that light and subatomic particles can behave both as waves, but also as particles. It means that the two states are not mutually exclusive. We knew from the 19th century that light could reflect, refract, and diffract like a wave. And Einstein's photoelectric effect experiment showed us that light could also behave like a particle. But then the Davison-Germer experiment showed that particles like electrons could also behave like waves. In his experiment, Davison fired electrons at a crystal lattice. Some electrons reflected from the outer layer of the crystal, and some reflected off layers further inside the crystal. The light that reflected from the lattice was analyzed and turned out to have light and dark fringes in this pattern. This was an interference pattern, showing that the different beams of electrons had interfered with each other, just like a wave, creating constructive and destructive interference. De Broglie put some math to wave-particle duality as part of his dissertation. He suggested that if something was a particle and a wave, then it would have to have both a wavelength, like a wave, and momentum, like a particle, and that these things would be related to each other. According to his equation, the de Broglie wavelength, lambda, of an object or particle measured in meters would be equal to Planck's constant h, which is always equal to 6.63 times 10 to the minus 34, divided by the momentum of the object or particle p, measured in kilograms meters per second. We should also note that the momentum of an object or particle is equal to the mass, measured in kilograms, multiplied by the velocity, measured in meters per second.
All right, guys, so you can see that kind of brings everything we've been talking about for the last couple weeks together. We mentioned the photoelectric effect, we talked about wave-particle duality, and this is sort of the last piece of the puzzle. So now that you watched the video, go ahead and complete the Google form for your grade. And if you want more practice, make sure you try the extension opportunity. I'll make sure I include some more problems if you want. And if you have any questions, email me at diana.rye@clevelandpublicschools.org. Good luck, guys, and thanks for working with me.